Everything I will talk about today is joint work with Soham Ghosh, who is my graduate student at University of Washington. I realize I have a generous 2-hour time to speak. I still have a 1-hour talk, so I hope there will be enough interruption that we go over time and take advantage of the extra. So let me start by background over C. These are things that I will build on. Let A be an abelian variety over C. It turns out things have a uniformization that will be a complex torus. Not all complex tori are abelian varieties, but some of them are, depending on some positivity condition. And many of the things I will talk about are actually correct for complex tori and in the graphical setting for real tori. I want to call this actually X, sorry, just to follow my notes. Any abelian variety has a dual. And over C, you can precisely say what kind of vector space and what kind of lattice you should mod out. But it's also useful to think of this as the space of line bundles with trivial first-Chern class. And then there is a duality between these, which is best codified by a line bundle on the product. So the point is, if I put my hand on a point here, I'm looking at the line bundle here, and vice versa. A point here, so X is X dual. The point here is a line bundle here, and you might wonder, can you package this information together? Is there a universal bundle on X times X hat? Got these two projection maps. It turns out there's something called Poincaré bundle, which sort of packages all this line bundle information. Namely, if you look at the fiber over some point on X hat, you actually get the line bundle that, so this is isomorphic to X hat, which is a line bundle as a line bundle. On X and vice versa, and you maybe decide that the point 0 on the first fiber should be the trivial line. So this is one way to fix the possible choices. And this leads to, so this Poincaré line bundle is very important. It codifies many dualities between X and X hat. And maybe let me draw a diagram, which is the starting point for the talk. So
which letters are lowercase on the right hand side of the board?
Yeah. Great. Thank you. So I should actually, so in the paper, of course, we have LaTeX and we have, this is MathCal and these are lowercase. And these are MathCals. So these are line bundles, these are the two projection maps. They call them pi 1 and pi 2. I'm worried I used pi later. Is this readable now?
There's also middle X hat and big X hat.
Yes.
What your questions?
Yeah. I ask you to use your imagination to think that. Yeah, I won't. Even if I try, I will fail. So. These are little x. I hope this will not be an issue going forward. There won't be too many repeated letters. Other questions, confusion? You can actually give a functor using this Poincaré line bundle, so-called Fourier-Mukai functor from the category of bounded complexes on coherent OX modules on X to X hat, which is equivalence of category. And the idea is if you have some complex here, bounded, I'm not going to define these objects, but these categories, but I won't use them really, but this is just for motivation. If you have a complex here, you can pull back with P1. So the F of, so just say F, the complex will go to, so the idea is you pull back along P1, you twist it with the Poincaré bundle, and then you push forward, except that you have to say derived. This is derived category, you have to say derived pull back, derived push forward, and put the right adjectives there. So you tensor the pullback of F, and then derive push forward 2. So the idea is always similar. You pull back, twist, push forward. Pull back, twist with the push forward. So I'm going to do tropical geometry, and at this level, things are hopeless. I'll come back to it. But there is a map, so-called Chern character map, to Chow on X and Chow on its hat. I won't define Chern character map, but like in very simple case, if you have a line bundle determined by divisor, this is essentially sending it to the class of the divisor. But I mean, there's a map that goes to the K theory and then to Chow, and F induces another map in this level, except the Chern character of the Poincaré bundle is the thing that you have to twist with, and it will have denominators, so I have to put a Q here because I'll have denominators. Already at this level, you have actually equivalence of categories because there's an inverse, more or less, by switching the role of X and X hat. So you can have a similar diagram which you switch X hat and X, and that will give you so how to go back, and that gives you equivalence of category. And this induced map at the level of Chow, the idea is again the same. You have a algebraic cycle, you pull back, twist, push forward. The twisting will happen with Chern character of P. And that also will be isomorphism. And you can say isomorphism of what structure? It's isomorphism of groups, even though these are rings. And don't complain, it's even better than isomorphism of rings because there are two product structures for Abelian varieties. One of them is the usual intersection product. But since you have a group, you also have Pontryagin product. And this map is more interesting than just ring isomorphism. It takes intersection product to Pontryagin product to intersection product. So it's a very rich isomorphism, but if I just want to use the word isomorphism, it's isomorphism of groups. So this is equivalence of categories. This is isomorphism of groups, but taking, as I said, intersection product to Pontryagin product, vice versa. And then
So F has co-dimension K to dimension K.
Co-dimension K. No, it actually spreads things, and it's important. So
it's not graded.
And it doesn't respect the grading, but that's why the Google stuff that we talked about it becomes interesting. So you will talk about, so it spreads things, but not at the level of cohomology. So this also is, so at this level, let me say tropical stuff is hopeless at the moment, at least. I realize people have talked about vector bundles in this year in this venue. We already have to settle what is a vector bundle in the context of tropical varieties. Of course, or major advances in recent times, but building a category of sheaves and the derived category and nice abelian category and all that is not within reach. I'm not actively thinking about building at this level. At this level, things are already interesting and useful and work in progress, both with my students and other collaborators as well. And I'm not going to talk about this level today, but what has been done is the lowest line in this diagram. We can also go to cohomology. I'm going to put Q coefficients here, but it turns out you can, in fact, Q coefficients because I already have tensored with Q, but it turns out you could do better if you try at the lowest level. And then you have another map. Yet again, if you have a cohomology class, you can pull back, twist with the first Chern class of the Chern character of the Poincaré bundle, and then push forward, and you get another map here, which is isomorphism. And this is the level at which I will talk about. So let me say tropically. This, I'm not hopeful we have all the setup. Here is work in progress. And one should even be more ambitious. One might be able to do this at the level of cycles, not just chow. And this has applications. People have been interested in this for a variety of reasons. But this is what I'm going to talk about.
On the top line, if you replace derived category with coherence with derived category of constructible, is there a corresponding?
And over C there is constructible sheaves, I think. I don't know a reference. I should admit this is not what I do even tropically, but at least in Birkenhacke-Lange, this theory is described only for coherent OX modules. My feeling is that you can't do it for constructible, but I didn't look up the appropriate references. Any other questions about the background? This is not what I do. I just wanted to mention. Oh, maybe one motivation. So Mukai, I believe, did this equivalence of categories, which is already sort of, it tells you that X and X hat are not isomorphic in general. But it's saying that derived category or all possible cohomology theories that you know is not going to be enough to distinguish them. They are derived equivalent, even if they are not necessarily isomorphic. I mean, X and X hat can be isomorphic. There might be a principal polarization certifying that, but they don't have to be. And nonetheless, they're always derived equivalent. So that's perhaps one of the motivations of Mukai to describe this map. And why it's called Fourier, I mean, formally it looks like a Fourier transform and there are exponential maps and things like that, but I'll leave it at that.
Is it more than formal? If you specialize?
I have, of course, I haven't seen any reference that actually does the Fourier transform. like classical, I'm guessing your question is, can you do this classically for maybe torus and then
Like, is it a special case, I guess?
I haven't been able to do it myself or find anyone. It's mostly by analysis.
I seem to remember that there was a paper titled Fourier-Mukai transform is Fourier transform.
I mean, it's certainly, if you're willing to, by Fourier transform, talk about abstract harmonic analysis, there is a way, I think, to describe this as abstract harmonic analysis. But if you want really e to the x, e to the 2 pi I x, I'm not sure if you can do that. Anyway, but that's not what we do today. If you are not interested in abstract nonsense, you can come back. I'm going to do things tropically, so tropical. Setup. I'm going to talk about tropical abelian varieties, or more generally, tropical analog of complex tori, which are real tori with integral structure. Let N be a lattice. By that, I mean not a posset lattice, I mean something isomorphic to Z to the G. And then NR to be the ambient vector space. And essentially, I want to look at the real torus that is obvious, but I'm going to use another lattice, lambda in NR, another lattice. So I have two lattices. And the point is, by lattice, I always mean full branch. The point is, not only I want to quotient out a vector space by a lattice, I want to have another way of saying what is a rational direction. In tropical geometry, we want to have like balancing conditions and things like that. We have to say, what are the integer vectors that I'm allowed to add? So I have two lattices. One of them will be used for my directions. Then a tropical abelian variety, or more precisely, real torus with integral structure. It doesn't have to be quote unquote algebraic yet. Actually, want NR mod lambda. This is a real torus, G-dimensional, with integral structure. By integral structure, I mean this other lattice that is codifying rational direction. Structure. Very simple object. Why would you study this? These appear as skeletal of Berkovich analytifications of abelian varieties. So these appear as so if you give me an abelian variety over an Archimedean field, I can analytify that. I get some object. But it does have a, in this case, canonical skeleton, which is an object like this. So it's a real torus with integral structure as skeleton, canonical skeleton of Berkovich abelian varieties. But the history of this is much older. It turns out these also appear purely over complex setup if you degenerate a family of abelian varieties to the boundary of moduli space. We can use the data of limit mixed Hodge structure to build an object like this. So this is prehistory in Faltings and Chai. This is announced as fact of life, and the entire book is written to generalize that picture. But we couldn't find a reference in a paper with Robin de Jong. We have described how this real torus can be made from Hodge theoretic data. I mean, vaguely, you can look at your period matrices and look at the limit of period matrix as you go to the boundary of moduli space. Period matrix is some matrix, and as you go to the boundary, you can imagine you will get up to some logarithmic blow up, you get some kind of a matrix. It's called an nilpotent orbit theorem, and that matrix sort of codifies these lattices for you. It's also as limits of abelian varieties, families of abelian varieties. Of course. I'm happy to give you a reference that this has been written down, but this is very old stuff. Okay, so that's tropical abelian variety, or more generally, I haven't. So not all complex tori are abelian varieties. It turns out for most of my talk, it's enough to work with these real tori, but if you have some positivity condition, this will be tropical abelian variety. But let me postpone that. In fact, I do need the notion of line bundles. Unlike vector bundle, line bundles are somewhat well understood in tropical setting, and in fact, for the abelian variety case, there are many different ways of thinking about line bundles, which I want to list. So these things come with a sheaf, with the structure sheaf. So I've been saying that I have this second lattice to tell me what is integer direction. You can talk about sheaf of affine functions with integer slopes, or sheaf. This is the so-called structure sheaf of piecewise affine functions with integer slopes. This can be done. I mean, we are used to piecewise linear functions in tropical geometry anyway. You can think what this means. But then once you have a structure sheaf, just like classical setting, you can define your line bundles as torsors over your structure sheaf. This is not the point of view that I want to use. In fact, for most of theory of abelian varieties over C, we are lucky to have some kind of a function theoretic explanation of line bundles, which I will get to in this list soon. But I want to just emphasize that over any tropical space, it makes sense to talk about this sheaf and also the line bundles in this language. You can also think of them as just like in, I guess, topology, you can think of them as a piecewise polyhedral space, which are locally trivialized. So this is a morphism of polyhedral spaces. Locally trivialized, but then you have to insist your gluing maps are sort of piecewise affine functions. A third point of view, which is again general, you can talk about Cartier divisors. And just like classical situation, they correspond to line bundles with a choice of a section. That also is general. But the one that is most relevant to this talk is so-called Appel-Humbert. I always forget. Appel-Humbert. So classically, what happens if you have a line bundle over abelian variety over C, you can pull it back to the universal cover and it becomes trivial. Then it turns out by this fact, you can use, so your Picard group with the isomorphism classes of line bundles over X will have a description in terms of group cohomology on the universal cover, and that can be packaged in a way that you can describe a line bundle using a Hermitian form and a semi-character. So you can describe a line bundle by just some Hermitian matrix and a semi-character, which is a function. So that gives you a very good handle on line bundles, which is extremely useful in proving results about line bundles. You can forget about geometry and just do functions. And this data in the tropical setting, in some form, I think existed in an earlier paper by Kensumi, but with Andreas Gross. We have a paper, it's called tautological cycles on tropical Jacobians or something like that, which we described this data because we needed to use it. So it's some kind of some symmetric matrix on an R. It's a symmetric bilinear form on an R with some integrality condition. This is analog of so-called Riemann form classically, and then some analog of character, which is some linear map, plus some linear map. Some matrix and a linear map describe line bundles in our setup. That's the moral of the story. I don't want to give the exact description of the setup, but just trust me that there's a very easy way to think about line bundles in our setup. Maybe the most important thing is that I realize many people in this room are well aware that positivity in tropical geometry is a difficult question in general, and it's an important question and it's difficult, but not for abelian varieties. You have a bilinear form, and you can ask, is it positive definite? Well, that will be your positivity. And if this bilinear form is not non-degenerate, you can say your line bundle is non-degenerate. You should think of this, and you will think of this, and I will write it down, that this is the first Chern class in a precise way of your line bundle, this symmetric form. Okay, so that's the notion of line bundles without giving details. Then another tool that I need, or another machinery that I need, is tropical cohomology.
How easy is it to go from 4 to 3, say? Somebody gives you a symmetric matrix that has some integral condition for lambda and some linear map. How do I think of that as like?
Let me describe this for Jacobians, which is something I think about most and it's easiest, or principally polarized version. If you give me the symmetric matrix, you can think of it like a metric on an R. I mean, that's like Gram matrix on some vector space. So you can think of this as a bilinear form on your vector space. Then you can look at so-called tropical theta function, which is, if you have a bilinear form on a vector space, this is the vector space. We can define a so-called theta function which sends an element z to minimum of z minus lambda, z minus lambda for all lambdas in. Lambda is a lattice. And then you want to kill you want a piecewise linear function, you remove this z dot z. So this is a piecewise linear function. Then you look at the corner locus of this. It turns out this has a name actually. So it will be the boundary of the Voronoi decomposition on your vector space. And that will define a periodic polyhedral object in your ambient vector space, which means it gives you a divisor on the quotient.
A divisor.
It's a Cartier divisor.
Corner locus of a piecewise linear function.
It's corner locus, it's a Cartier divisor. And that will be your Cartesian. I mean, what I said was not really about Jacobians. Any principal polarization, this will be fine. In non-principal case, this can be done too. Just I can't be as quick to describe. I must say this is not, there is some normalization. If you want to ever talk about theta functions, look up exact definition. There should be one half of functions that I didn't want to worry about right now. And I think this description is absolutely clear. Whereas the other description would be a little bit more work. Okay, but the moral of the story I want to remind you is that for tropical abelian varieties, things are more manageable because of 0.4. You can actually even talk about ampleness pretty easily. So the next thing I want to talk about is, I should have put some titles. This was tropical real tori or real tori. This will be and then now tropical cohomology. Or homology. This is rather technical to describe all the nuts and bolts, but luckily for abelian varieties, I can actually explicitly say what it is. The idea is, so let me just say the idea, but very quickly I'll switch to abelian varieties, which things are getting easier. So you might want to define your omega-1 to be the structure sheaf modulo the constant sheaf. And then there is an omega p version of that, which almost you would like to say it's the top wedge product, pth wedge product of this, but it's a little bit subtle. So I will lie and say this is pth wedge product of omega-1, which is almost the case, but you have to restrict to the regular locus and then push forward. Let me not dig a hole. And then you would like to define HPQ as HQ of omega p. And modulo some subtleties that I'm sweeping under the rug. This is the definition of tropical cohomology.
What is the regular locus in our setup and X?
So you should look at all points that, so in this case, everything is regular actually. But
X point is regular.
yeah. But in general, you have to look at points that their neighborhood are isomorphic to Rn, which is the case for every point here.
So
But even here, you might want to worry about cycles within your space. Then you will have, for abelian variety, everything is regular. But if you have a cycle in the abelian variety, then you might have a star-shaped point that you want to worry about when you take this cohomology class. Okay, so this is an abstract definition. This is just old-fashioned sheaf cohomology, nothing tropical in this last line. But for abelian varieties, things are easy because just like the classical setting, you can actually describe it in terms of the lattices involved. The classical situation also, the cohomology is described entirely in terms of the lattices that appear. Let me give me a second. Let me find where I am on my notes. I have to give reference. I'll answer a question, but I wasn't faithful to the reference. Go ahead.
Do you use the integral structure in the definition of this cohomology?
No, this is So this definition is for any tropical space.
But that thing that you're pointing right now, that's like a finitely generated abelian group or a vector space over some field.
This is a vector space. It's a vector space. It's a Z module actually.
Yeah, it's a finitely generated abelian group.
Yeah.
It's different from.
But I mean, like when you write X,
Yeah.
you use the integral structure, right? When you define this real torus together with the integral structure.
Yes.
Affine must.
Affine X
Yes.
depends on lambda.
Ah, I see.
Integer slopes. Okay.
So when you mod out by the Rx, do you mean like Zx?
Rx.
Constant functions.
Constant function. So affine fx is the slopes are integer, but the shifts are real. And I want to kill the shifts that are real. I'm not killing the slopes.
You're killing slope 0.
Yes. Good questions. Before I forget, this is the work of
Ittenberg, Katsarkov.
Ittenberg, Katsarkov, Mikhalkin, and Jarkov. This was announced 2000 late 2000s, and the paper appeared later in 2015 or 16. I realize Chris Shaw gave lectures in one of the workshops here. I have a paper with Andreas Gross that sort of studies this from a sheaf theoretic point of view, because so things are very explicit in the prior work, and proving things like Kunev formula and things like that are very hard when you do things explicitly. So we kind of wanted to use the big machines, and we wrote a long, painful paper to build that machine so that you can use sheaf theory to prove things about. So that's the history. The reason IKMZ paper was interested in this is very nice application that if you have a nice degeneration of a family of varieties going to the boundary, and if your dual complex at the boundary is nice enough, it's tropical manifold, then HPQs in the limit actually can read the HPQ of a generic member of the family. Somehow they wanted to build. That's one evidence that this is the correct notion of HPQ tropically. Then there are further developments that there is also a form or current version of this using Lagerberg forms. There's a paper by Shah, Smaka, and Rao, I think, that shows that with real coefficients, you can actually do this using sort of Dolbeau type cohomology theory.
When you talk about like limits of abelian varieties in the previous Blackboard, is that degeneration nice in the sense of
No.
IKMZ?
No, this is a constraint setup. So any semi-stable degeneration, I think technically you should go. So AG has many different compactifications. What I have in mind is second Voronoi compactification of AG, and the limits, one parameter limits of that. That's the setup that I have in mind. Here, there is a further constraint that you can't just go to any point in the limit. It should be a semi-stable degeneration that goes to a limit whose dual complex is tropical manifold, meaning it's locally matroidal.
So their main theorem just do not
constraint.
directly apply to this
Yes.
type.
This is more constraint setup.
But Farbod, if the skeleton in the limit on this middle board is a real torus, then that's going to satisfy the hypotheses for IKMZ.
So this is in the abelian variety case, yes, but this theorem is not for abelian varieties. This for any projective semi-stable degeneration. Yes.
Maybe my question was.
I apologize. Yes, I didn't understand. So for abelian varieties, the limits are nice. But for more generally, if you want to read HPQs of degenerations of other type of varieties, you can if you're lucky. And needless to say, these are all sort of goes back to the origins of certain approach to tropical geometry was sort of working out the details of Kontsevich's approach to disproving Hodge conjecture. That's a different story, which I have nothing to say about. Okay, let me now say what is the first Chern class map. Oh no, I lost track. I have to say what's the situation for abelian varieties. If X, so X in that board was not necessarily abelian variety or tropical abelian variety. If X is tropical abelian variety, it turns out H11, let me write that because I need it most. It's going to be isomorphic to lambda dual tensor n dual. So by dual, I mean Halm to Z. And more generally, HPQ, and this is a feature for abelian varieties even classically, that if you understand the first cohomology, then you understand all cohomologies. This is going to be, look, I hope it doesn't look terrible. This is a wedge product. My lambda actually has a leg. So it's going to be P copies of lambda dual and then tensor Q copies of N dual. I'm not going to work with HPQ much. Is it readable? Okay, so if you missed Chris's talk or I'm being too fast, this is the type of cohomology I'm working with. It's very explicit again. And let me say what is the first Chern class map. So you have this projection map, and this is called omega 1 now. Well, this induces a map on cohomology. So you can look at H1 of X comma F. You get a map to H1 of X omega 1. And I have now called this H11. And it turns out the cohomology approach, the fact that pulling back line bundles from the base to the universal cover make them trivial, gives an identification of this with isomorphism classes of line bundles on X. This is the phenomenon for abelian varieties. So X is tropical abelian variety. And you can show this isomorphism by some check cohomology argument, which we have written down with Andreas Gross. And you might want to call this now, so this induced map, you might want to call this C1. This is the first Chern class map. This is almost like what you do to the exponential sequence over C classically, unfortunately, and it's a big regret that we do not have the actual exponential sequence tropically. But at this level, this exists. So this is the connecting, this is the presumed connecting homomorphism for the exponential sequence. But the moral of the story is that if you give me a line bundle, I can produce an element in H11, which, by the way, H11 is like this, which you can think of it as Halm from lambda to n dual, which is more or less a bilinear form on n. So that's what I said in the Appel-Holmberg data. If you give me a line bundle, I can produce some matrix which is symmetric. That comes from this construction. You have to maybe fix spaces for lambda and then dual and work it out. You see that what you get is precisely a symmetric matrix with some integrality condition. So a line bundle on tropical abelian variety will produce a symmetric form for you.
What do you know about the kernel and co-kernel of the trunkless map? C1.
I mean, anything you know classically for complex abelian variety is more or less true tropically as well. I don't know how much detail you want, but you hit. So the kernel certainly is not trivial. That's why you call peak zero. That gives you the entire dual abelian variety, which you can completely describe in terms of n and lambda. So kernel is completely understood. The image. The image is precisely the sort of Néron-Severi type argument. These are precisely the symmetric forms on NR that are integral on that are integral on lambda times n. I might be dropping some duality, but the image is precisely the so-called Néron-Severi, tropical Néron-Severi, which is a Riemann for tropical Riemann forms. My guess is you're also wondering Hodge type questions, and for that I should refer you to a paper of Chris Shaw and Lefschetz one-one forms. I think I'm dropping the name of co-authors. Maybe is it Shaw, Smaka, Rao, or Yell? Shaw, Rao, Yell, and Shaw, Rao, Yell, Shaw, and permute the first letters. Have written a paper about what Lefschetz one-one theorem.
So you're saying that C1 is sometimes surjective and other times not surjective, depending on what lambda is.
Right.
Then there is
lambda. Yes, I suppose you can make it surjective, but in general, I expect it shouldn't be surjective. It should be symmetric forms. So if you think of this as all symmetric forms, yeah, these are symmetric forms. Sorry. Yeah, let's talk after. I'm a little bit confused. Let's talk later. I think the right paper to look at is by Yell, Shaw, and Rao. Okay. Now I can actually write our first theorem. Maybe I call this a lemma. There exists a unique opto-isomorphism Poincaré bundle. X times X hat. X is it turns out the dual also has a, so this is big zero of X because of the Appel-Humbert data, you can actually completely describe this, which is answering half of the question June just asked. What's the things that first term class are zero, the kernel? This will be the dual R modulo and dual. Answered half of your question. This is the kernel of C1. Okay, the proof of this is half of it is trivial. Existence. Use Appel-Humbert. So you have these two things, and their product is also a real torus. And there are obvious symmetric forms and linear forms on these. So you need to produce a symmetric form and a linear form to describe a line bundle. And we write this down. The linear form, actually, I can tell you right now, it's zero. Function zero. The fact that n and lambda are dual gives you an obvious bilinear form as well. So we write this down. The uniqueness is a bit more work. So classically, there is a thing called seesaw principle, which uses techniques that doesn't exist tropically. So we prove a weak seesaw principle. I call it weak because it only works for Abelian varieties, and we actually use Appel-Humbert again. That's why it doesn't work for beyond using Appel-Humbert. But the moral of the story is that you have a line bundle here that you can work to write duality, which I will do right now. Theorem A. So everything, all the theorems I will write is with Soham Ghosh. The map on tropical cohomology given by, so I call this F for Fourier. I have this bi-graded cohomology theory. So a cohomology class, do exactly as in the classical setting, pull back. So you have x times x hat going to x and going to x hat, P1, P2, and I just said there's a Poincaré bundle there, P. So pull back with P1, twist with P, but you have to look at exponential of the first Chern class of P. I'll say what exponential is, and then push forward. P2 doors. This is a map gal P. Maybe I should have used different colors. I think everything in this expression is clear. So pull back a cohomology class, exponential I explained, C1 I explained, P2, the bi-graded cohomologies, there's an abstract definition, but it's very explicit for Abelian varieties or real tori. Exponential is just formally the summation. So e to the use e to the x is x to the I divided by I factor. And it turns out this is a finite sum because a high enough intersection will be zero. It's a polynomial. The statement is not finished, so there is. I just wrote this down, but what do I want to say? Please go ahead.
But when we talk about push force in tropical cohomology, is it defined using some Poincaré duality, or is there a separate definition of push force?
It's a separate definition. It's a direct definition which you can find in our shift theory paper. It's very similar to the classical one. Let me finish the statement. This is well defined. That's a mild statement. But the main, and it's related to Poincaré duality now, and the restriction from HPQ of X, it turns out, so this is restrict to this piece, F restricted to HPQ. It will land in HG minus Q, I think, G minus P of X2R. So part of the statement is that if you restrict, you will land here, and this will be an isomorphism. Is an isomorphism. Of groups. Okay, so this is an analog of the last line in the classical diagram that I have now erased. But back then, I wasn't talking about HPQs, I was talking about rational cohomology, cohomology with rational coefficients. So what's happening is, even classically, if you tensor with C and look at your Hodge decomposition, you can ask whether you have such an isomorphism, and the answer is yes. So we are sort of digging deeper into the Hodge filtration. And I think Bouville observed that this isomorphism exists. And we are saying that tropically, this isomorphism also exists. And the proof of it is very close. In fact, this map on the restriction map is closely related up to some map from X to X dual. It's closely related to Poincaré duality map, which is a result we had proved earlier. Let me make a couple of remarks. Classically, these folds. And the second remark is that this isomorphism is closely related to Poincaré duality. Which is something, depending on the level of generality, I have proved with Andreas Gross. So we prove actually a Verdier duality, and then we show that in the cases that you have a tropical manifold, piece locally it's matroidal, and the Verdier duality actually, the dualizing complex is concentrated in 1 degree, and you get a sort of Poincaré duality statement, which is a consequence. But Poincaré duality in the language of forms and currents was proven by Shaw, Smaka, and Rao. So I have to be more careful with the orders. Smaka. I hope I'm referring to the right paper. And then they had in the same paper, they proved that the cohomology theorem I'm talking about and the Dolbeault version are isomorphic. So if you put them together, you do get a Poincaré duality statement that I'm talking about.
I'm confused why the restriction lands on G minus.
Yes, so the Poincaré duality actually lands in G. So H of G minus P, G minus Q of X. Then you want to go from X to X hat. And the map that uses that switches.
I think my confusion is more basic. Why does it land on a single graded piece?
Oh, yes. So it's probably caused by the fact that I said in the Chow version, the grading spreads. It's a fortunate or unfortunate fact that at cohomology level, things are respectful. The grading is respectful.
I mean, if alpha is 1, then I have like exponential of the Poincaré line.
So P also is concentrated in 1 degree.
But I'm taking exponential of that.
Yeah.
So I have a 1 plus
Yeah, I see.
P plus P squared
Yes,
over 2
yes.
and so on. And then I'm pushing forward that.
Yes, that spread somehow cancels each other. The same vision that you have explains that in the child level it will spread, but the magic is that at the cohomology level there's a cancellation. The sort of the contribution from P will not. It will cancel each other, so it comes into the proof. It's a magic. It's not intuitive.
Did you say what the reference is for the classical version of this statement?
I think it's in Bouville. I'm pretty sure Bouville proves it. But I think in our paper we do give a reference. Let me. Yeah, this is a classical. It's a result of Bouville. Yes, and your intuition about this is this must spread is absolutely correct at the level of Chow. Cohomology, things cancel magically, so there's a magic involved.
What happens with the cycle class map? There should be a cycle class map from Chow to cohomology.
Yes,
If things spread out in Chow.
but that map is not respecting the grading at the level. Does it respect the grading?
Yes.
You're saying I mean, now we have a bi-graded thing.
Maybe I'm just generally confused, but maybe we can talk later.
Yeah, I'm pretty sure. Well, the statement is absolutely correct classically. That's a Bouville result. I'm quite sure our result is correct. In any case, it's on the archive, so it must be correct. But I mean, at least in the situation that the degeneration happens, you expect HPQs, weak HPQs, and duality should also go to duality limits.
That should probably be checkable because C1 is in cohomology. C1, the cohomology is kind of simple in the classical case. Maybe in this tropical case, it's not so trivial to check. I guess C1 could check for alpha being, one could actually just verify this. I mean, I'm not suggesting you do this now, but for alpha being the identity, one could probably just check this by hand
Yes.
in the classical.
Yes. And also here, I mean, everything is very explicit. So you can actually write down the first chain class of P in terms of, you can fix a basis for lambda and n, and then you can write down the first chain class of P explicitly in terms of some tensors given by the bases, and you can write down everything. Yes. In fact, all the proofs, all the theorems are complete computational. You write down formulas for all the identities. Okay, so that concludes the sort of the Poincaré the Poincaré bundle and Fourier-Mukai transform at the level of cohomology is this. What I want to do next is to give yet again the word Poincaré appears, but it's a very different result. So, Poincaré formula. Should I take a break or should I continue? I think I have maybe 20 more minutes, but
It's up to you.
audience is not tired. I can continue. I don't need a break. Continue. This is also like any other theorem I write down is joint work with my student Soham Ghosh. So let's pick a line bundle, which is non-degenerate. By which I mean the C1 of the line bundle is some symmetric forms and some matrix which is non-degenerate. That's the luxury I have for Abelian varieties. Then let's look at actually the C1. Let's call it E. By the way, this is just a reminder. This was in H11, which is described concretely. These are all isomorphisms. So you can think of this as a very concrete object, and we do in our proofs. So it's a bilinear form, gives you a bilinear form on NR with some integrality condition. Bilinear form on NR with some integrality condition. So this is one input. Then you have two ways of sort of cooking up objects on the x-dual side. You can apply Fourier-Mukai, or you can apply the so-called polarization map. So this map phi can be cooked out. So you have a map from x to x hat, and it sends, let me not use, let me use z, sends it to so this is translation by z. So if you give me a line bundle, there is I pull back with respect to a translation by z. I get another line bundle, and then tensor it with L inverse. It turns out this object will have first term class 0. Again, by Appel-Humbert, you can show that sort of the data of translate is closely related to the data of the original L. And this is an isomorphism. There is something called theorem of the square classically, and tropically also you will prove using Appel-Humbert again. There's a theorem of the square. This is a homomorphism. This is a theorem of square. Which is in our paper tropically, but follows the same recipe. This is a homomorphism. So there are two ways of taking things from X to X dual, objects on the X side to the X dual side, using the so-called polarization map, or using Fourier-Mukai. And the theorem that we prove is that these two are highly compatible. And this has a name. This turns out this identity is generalizing some very interesting formula from Jacobian case to all Abelian varieties. Again, classically, this is a result of Bouville, which we are doing tropically. So the continuation of theorem B. for all k between 0 and g. G is the dimension. We can look at the first Chern class of L and then look at its kth intersection coproduct within the case of when you represent it as an element of n dual times lambda dual is some kind of a tensor, and you can look at the kth self tensor of that. And then you can apply Fourier transform to this. It turns out up to some k factorial. Or you can look at, so this will be in G minus k, comma G minus k. I mean, before Fourier transform, it will be in HKK because I start with the H11 and tensor it k times. And then Fourier-Mukai would flip. Luckily here k and k are equal, so you don't have to remember the flipping that side, but it's G minus k, G minus k. So this thing is in G minus k, G minus k. But you can do the following as well. We can look at G minus k times product of this, G minus k factorial, and then just push forward with respect to the polarization map. That also takes things to the other side for you. There's a homomorphism between x and x dual that induces a homomorphism from cohomology of x to cohomology of x dual, and you can use that. And the question is, are they equal? And the answer is yes, almost. There's some housekeeping. There's a -1 to the G minus k, and then determinant of E. And this is actually interesting. E is symmetric form. You can think of it as a matrix. You can take the determinant of it, and you get a number. Okay? And this number is very closely related. It's actually degree of the polarization. So it's closely related to how bad this map is. If it's an isomorphism, determinant of E is 1. If it's not an isomorphism, it's a map of degree D, and D is the determinant of it. Let's say if L is ample to be careful. I'll get back to that. So this is an important contribution. Let's say for Jacobians, this number will be always 1. So the two numbers are almost the same, except for this -1.
Was that also related to H0 of L?
H0 of L. Oh, yes, you're ahead of me. Yes. There's the answer is yes and no. If it's ample, the answer is yes, absolutely. If not, then it's very different and very mysterious, and it's related to Riemann-Roch, Mumford-Kempf vanishing theorems. In fact, maybe it's a good time to. I'll just write that down now. So in our paper also, we have some discussion about Riemann-Roch theorems for tropical abelian varieties. We just advertise that Riemann-Roch theorems in tropical geometry are very rare. There is one Riemann-Roch theorem known, to my knowledge, completely for graphs or tropical curves. But even there are mysteries. Riemann-Roch for tropical abelian varieties. For L ample, again, ampleness is not easy to describe, but in our situation, it means that what I call E is positive definite. we have, maybe we should call this proposition or theorem. We have determinant of E is H0 of X. L. So you can look at the space of global sections of L, but this is a very mysterious object. It turns out so this is very difficult, but Kensumi, in a relatively recent paper, proves that H0 of XL is actually a convex polytope. And moreover, he shows that the dimension of this convex polytope is equal to what Dustin Cartwright defined. So let's call this Baker-Noreen. Definition of rank. So Baker and Noreen did some combinatorial definition of rank for graphs, or finite graphs, in fact, which was extended to metric graphs and tropical curves by Mikhakin and Jarkov. And in a paper by Dustin, this was extended to higher dimensional tropical complexes. I think the paper is called Tropical Complexes or something like that. And he was trying to prove inequalities coming out of presumed expected Riemann-Roch theorems that should be out there. So this is the definition of Cartwright. And even for graphs, these things are not polytopes. These are polyhedral spaces, but they are not even pure dimensional. There is no way to make connection between dimension of that polyhedral space and H0, but it turns out for Abelian varieties, this is done. This is done by Kensumi. And in fact, this is really, okay, the version that we are writing, you will not find it in his paper. So we write it in our paper, but really Kensumi had done this, he didn't write it down.
What is the ambient vector space of this polytope?
The space of theta functions. So you, just like classically, you have sections of a line bundle can be described in terms of theta functions on the universal cover, and they give you space because I described one of the theta, so it's a space of functions, and it turns out there are extremal points that can be described using Legendre transform, and he checks that the convex hull of those extremal points is all points. So this theorem is essentially, so this is, I take some credit, but really this is essentially results fleshed out. We do say something more about Riemann-Roch in our paper, but this answers the question by June that this determinant of E is related to the space of global section, but only for ample divisors. So why? Even classically, when things are not ample, then you have higher cohomologies, H1, H2, H3, and you can in fact completely describe which cohomologies are out there, which one of them are non-zero, the dimensions of them can be completely described. And there are vanishing theorems that at some point they should die. And that point depends on how many eigenvalues of positive and how many positive and negative eigenvalues E has. But under ampleness condition, you expect that all high cohomologies are zero. So this is really Euler characteristic. So this is the ample case, this is Euler characteristic of that. And I already said it, we do not know what is H1, what is H2, H3 in tropical world. So somehow we cannot write any Riemann-Roch theorem. Even for graphs, the statement is H0 of D, H0 of a line bundle, minus H0 of the dual of the line bundle. So we presume there is a third duality. We only understand H0, we do not have H1. So that's an obsession of mine, which I can't resolve, but things are nice for Riemann-Roch or Abelian varieties that are various vanishing. I think this is a good starting point to, so Abelian varieties should be a fair law. I expect if we ever understand higher cohomologies, we should start with Abelian varieties, not even with graphs. There's a lot of structure and a lot of Hodge theory actually is involved classically. So maybe we are ready to study this. Maybe let me advertise corollary of the two theorems, theorem B and C, is that we can also show something called geometric Riemann-Roch. Namely, H0 of XL in the above case, L ample, is some integral is, let's say, degree. In a precise way, some integral of the Lagerberg form. That's unfortunate. I want to introduce a new notation, I guess. This is not the first term. So this is the Lagerberg form. This is a form associated. To this is not a class. The previous C1 was a class. Now it's a form representing that class. There's a I mentioned this sort of the wrong approach to cohomology as well. And we are essentially saying the consequence of this theorem is the fact that you can interpret determinant of E as integral over that form. So this is vague, but
G wedge over C1.
yes, GG.
And shouldn't that number be just the same as multiplying in homology of the first chunk class?
Correct. It is the same. That's what we are.
Yeah, but then you could have just stated using without mentioning Lagerberg form, right?
I want to actually correct. I could have stated that, but I want, yeah. Sure, I don't have to, but there's a reason that I would like to think about that isomorphism as well. Or we don't know anything beyond what I've written. I mean, I wished, but I don't think the tools are there. The question was, do we have a Grothendieck Riemann-Roch? And the answer is I don't know. Let me end by saying that, so what is this? This formula looks complicated. Even classically, why would Google look at this? And tropically, this is also true. It turns out one of the consequences of this theorem was a conjecture by Zakharov and Felix Rohrer, which comes for free. So some consequences, some other consequences. One consequence was already this geometric Riemann rock. But let me give you two consequences. If gamma is a metric graph, or graph, or abstract tropical curve, there is a tropical abelian variety attached to it, which is the Jacobian of gamma. There exists a Jacobian of gamma, which can be described in terms of chip firing. So this is equivalence classes of chip. This is 0 modulo chip firing. Or you can think of it as space of real flows, which is a vector space on the graph modulo integer flows. Maybe you want to think about just real homology with real coefficients modulo homology with integer coefficients. That's ultimately just flows. It's a real course. Then there's also a Abel Jacobi map. So Q fix a point from gamma to Jacobian of gamma, which using the Picard definition sends a point T to the equivalence class of A minus Q up to chip firing. Using the flow definition also, it's not too difficult, but a little bit harder to write down. But so there is this map, and you can look at the image of this map. Image of IQ. You can call this W1. If you think real note, this is W01. Things that are effective. And then you can do this also for WI. So you can define WI to be W1 plus W1 plus W1 G times I times. Alternatively, you can look at the product of gamma with itself I times and look at the induced map. Then the Poincaré formula says WG and W1 are related. And you can think of gamma as being the curve, and everything I say is true for a classical situation. And that's the background. Turns out WG minus 1. So WG is going to be the entire Jacobian. Just my classical case, this follows from Riemann rock or some other argument. WG minus 1 is essentially theta divisor up to a shift. This is called Riemann constant. Again, this is classically true and also tropically true. This is Mikhalkin and Jarkov in the tropical case. And theta divisor is actually the corner locus I was talking about earlier. You can look at the Voronoi decomposition. This is boundary of Voronoi. Boundary of Voronoi. Okay, and the Poincaré formula both classically and tropically says in tropical homology or cohomology, let's say homology. I'll put cohomology. You have the identity G minus I the class of Wi is the same as class of theta to the power of G minus. Well, this classically is called Poincaré formula. I'm not sure in what language Poincaré wrote this down, but he did many things. What's that?
W1.
So this is I, I'm sorry.
That's I.
That's I. And this has very serious applications. I mean, already the fact that theta to the G divided by G factorial is class of 0, which is 1, is closely related to what I was trying to say here. It's closely related to the fact that you have a principal polarization. It's a the case G equal to I is a consequence of Riemann-Roch. This is some kind of a more sophisticated version of that. And classically, I don't know the history, but it's called Poincaré formula, and tropical version of it was an earlier paper of mine with Andreas Gross again. That formula generalizes this to all Abelian varieties. So in this case, we have to be a little bit clever. We have to be very careful about how to pick certain bases. But it turns out the proof of that avoids cleverness. It uses some fantastic determinantal identities that I had to learn. But not much cleverness is involved. It's just the right proof. Theorem, what was the name? Theorem B generalizes this. And the classical version of Theorem B, due to Bouville again, was motivated by the same Poincaré formula classically. But then, in an interesting twist, you can try to prove a version of this for prime varieties. So if you have two curves or two tropical curves, you have Jacobians and you have induced maps between Jacobians, and you can look at the kernel of the induced map and you get something which is called prim. The Jacobian is attached to one curve, prim is attached to two curves. And the dream is that can we really not understand all Abelian varieties in terms of curves, maybe higher degree maps and things like that? Instead of, I didn't say for prim, you have to have a 2-to-1 map. Maybe you dream that all Abelian varieties come from a collection of curves. And that's the first step in this process. So let me be more vague because it takes us off track. There is prim theory due to many people, tropically as well, attached to the 2-to-1 map. And there are many names that I hope I don't miss. I think Sam can help me if I miss. Yoav Len and Dave Jensen. I know I want to end with Roland and Zakharov. Sam, do I need to add more names to this list of prims? These are the names I remember. I'm sorry, since it's being videotaped, I'm a little bit self-conscious. There's a theory of prim varieties, and in fact, this last paper had a conjecture. So there's also, Len also with Zakharov had a paper, at least their name has appeared here. There's a, instead of oval Jacobi map, there's a prim map. And a conjecture about the image. Similar and a Poincaré type identity. So in words, you have another map from this double cover going to the prim, and you can write polyhedral spaces there. And there was an identity conjectured by Rorley and Zakharov that some identity should hold in tropical homology or up to numerical equivalence. And it turns out we were lucky, we were not trying to prove that conjecture, but it turns out their conjecture is actually a special case of our theorem. So last theorem, theorem ECD, theorem D. Rorley Zakharov conjecture holds. Conjecture is a special case. Of theorem B. Okay, that's all I have to talk.